And I'm going to take a different tact on this idea of the binomial distribution. Remember, you saw that very complicated formula for calculating binomial probabilities. Binomial means that the value, that the variable can have two values. So for instance, if I were to plot the age for a population, that would be a scalar or continuous or numerical variable. And that would give me if it's normally distributed, it would give me a bell-shaped curve. Okay, now the binomial side of this is a variable that instead of having all different kinds of values, instead can only have two values. So for instance, left-handed or right-handed, right? So in other words, what's the probability that you would be left or right-handed in a certain population? So if a population has 85% of the population is right-handed, what's the probability that you would be right-handed if I picked you out of that population at random? Well, there's only possibilities for each person in there, either right-handed or left-handed. So the problem is, since 85% of the population is right-handed, then you would say that the probability of an individual picked randomly from that population is 85% likelihood that that person will be right-handed. So now, what about if I picked 3 people from that population? This may sound a little bit familiar now, right? If I picked 3 people from that population, what's the probability all 3 would be right-handed? Well, it would be 0.85 times 0.85 times 0.85. We kind of went through that in the second session, I believe, right? Now, what if I asked you, what if we picked out 7 people? What's the probability that exactly 3 out of those 7 are right-handed? Oh, well, my goodness, now this really gets complicated. If it had been all 7 are right-handed, it would have been 0.85 times 0.85 times 0.85, and so on. But now with 4 out of 7 being right-handed, well, a lot of things can happen. The first person I picked could be right or left-handed. Second person I picked could be right or left-handed. Third person. So we could have the first person, the third person, the seventh person, the sixth person, all right-handed. That would satisfy that. But also, a second, third, fourth, and fifth right-handed would satisfy it. Well, what about if the fourth one's not? Well, it could be the first, second, and third, and the fifth. So, but there's so many possibilities, and that's what that formula showed you. That formula we calculated the probability based on the number of the sample size or the number of attempts, right? Which was 7, because we're going to pick 7 people, and the number of successes that you're interested in, probability of successes. In this case, the one I just described, the probability of success in any individual that you selected from that population is 0.85 for everybody in that population, because you're randomly selecting them. So we know that satisfies that first condition, that the probability is the same for everybody being right-handed or left-handed in that population. So next we have to be concerned in, well, what do we determine as our sample size, or in this case we call it the number of trials. Our sample size is 7 people, and we're interested in knowing what's the probability that exactly 4 out of 7 would be right-handed. So our probability is 0.85 for anyone being right-handed. The trial size is 7, and the number of successes we're interested in is 4 out of those 7. So I'm going to demonstrate how we might calculate that. And we can do it from a table. We can do it from that formula. And you can see from that formula, it could get very tedious trying to calculate it from that formula when you get into large factorial values for exponents. In fact, Levi mentioned that there's one version of it that he showed you. In fact, our normal computers would not be capable of solving the problem. Okay, now we're not normally going to get involved in too much like that, but I'm going to show you a better way of calculating those probabilities that'll save you quite a bit of work. And I'm going to do that by opening Excel for starters. And I thought I did, but nothing happened. Well, it's bouncing up and down. Here we go. Come on. Here we go. Okay. Okay, here's our Excel spreadsheet. Let me blow it up a bit. Okay, so I'm gonna actually maybe make this just a little bit smaller. Okay, I think this will work out a little bit better for us. Okay, so we have a function in Excel that's called binom dist equals binom dist, binomial distribution. Okay, and I'm going to hit parentheses now. And when I hit parentheses, Excel gives you a hint on how to use this function. Okay, so binom dist is the number, first thing it wants is the number of successes, comma, the number of trials, comma, the probability of success for any individual, comma, and then something called cumulative. Well, okay, so I'm going to do my best on this. I'm gonna go before I actually type this in. I am going to go over here and I'm going to say to myself, I'm going to take a population where the prevalence of diabetes is 10%. Okay, and I want to know if I randomly select, if I randomly select 10 people, what's the probability that exactly 3 are diabetic? How about this? Let me, rather than 3, exactly 1 is diabetic. I chose that because that's the most likely outcome, right? 10%, got 10 people, 10% population is diabetic. So 10% of 10 is 1 person. That seems like the most likely outcome, doesn't it? Okay, so I'm going to go back here. I'm going to say to myself, okay, let's calculate that probability. So binom dist, parentheses, number of successes. Okay, number of successes. What's probably going to get 1 person that's diabetic out of my comma? Number of trials is 10, comma, and the probability for any individual being diabetic is 10%, 0.1. And then we have something called cumulative. I'm going to type in false, right here. We'll worry about why I'm typing in false in just a little bit. So I'm going to hit enter. And the probability of you getting exactly 1 person out of 10 being diabetic is 0.3874, about 39, almost 39%. What about 0? What's the probability that none of these people would be diabetic? Well, you could actually calculate that, couldn't you? Because the probability that they're diabetic is 10%. Probability that they're not diabetic is 90%. So you could say 0.9 times 0.9 times 0.9 times 0.9 10 times and get that probability. But we can use binomial distribution to do that also. Distribution up equals binom dist, parentheses. I'm going to put in number of successes this time 0, comma, number of trials is 10, comma, probability any individual being diabetic is 10, comma, and I'm going to put in false again and hit enter. Oh, that's pretty interesting. It's just a little bit less, isn't it? So this is what it would be for 0 people out of 10. This is what it would be for 10 people out of 10, 1 person out of 10. Well, how about if I want to know what it would be for 2 people out of 10? Let me center this just so it looks a little bit better. Whoops. Okay. So let's do it for 2. Actually, you know what I'm going to do? I'm going to put 2, 3, 4, 5, 6, 7, 8, 9, and 10 in that column. And over here, I'm going to calculate it for 2 equals binom dist, parentheses, number of successes. Instead of putting in 2 now, I'm just going to click that cell. Oops, I forgot to put parentheses in. I'm going to click that cell. That's the number of successes is B2, what's in B5, 2, comma, number of trials is 10, comma, the probability of the individual trial is 0.1, and then I'm going to type in false again and hit enter. And there's the probability we would get 2 people out of 10 that are diabetic. Notice it's a lot less than 1 or 0 because there's only 10% of the population is diabetic. Well, let's calculate this for every possible outcome. And there's all the possible outcomes. This number here is 9 times 10 to the minus 9. In other words, 0.00009 zeros and then 9. And 1 times 10 to the minus 10. Okay, so let's see what if I were to add all these probabilities up. If I were to add all these probabilities up, this is all the possible outcomes that I could have for this situation. Right, I'm going to try this again. Jump the gun on me. Good, let's try this again. I slipped. If I'm going to add this all together, what do you think I'm going to get when I add all these different possible outcomes together? Do I have somebody that's willing to take a guess at this? I'm going to enter as equal to 1, right? Ah, good, thank you. You got it just as I was hitting enter. Okay, right, 1. Okay, so now what if I were to ask you, what's the probability of getting 2 or fewer diabetics if I chose 10 people? Well, 2 or fewer, that would be this plus this plus this. So 2 or fewer equals the sum of these 3 values, these 3 possible outcomes. And that's 93%. Chances of getting 2 or fewer diabetics out of 10, if I randomly select them, is 93%. What's the probability of getting 3 or more diabetics, right? Well, 3 or more diabetics is going to be equal. There's 2 ways I can do that. One is to just take the sum of all of the possibilities that give me 3 or more. And that's 7%. Or I could have just said that that's equal to 1 minus the probability for 2, 0, and 1. Oops. Why is it complaining here? 1 is equal to 1 minus this value, okay, which gives me the same thing as the formula gave me here. Well, you want to know something interesting? Each one of these, I typed in the value false. False means that the question that's answering, I'll type this in here, equals binomial dist, parentheses. The question it's asking is cumulative. What it's asking you is, do you just want the value for that specific outcome, exactly 2 out of 10 diabetics, or do you want the cumulative outcome for that value and everything lower than it? Well, let's see what happens if I do this. Binomial dist is equal to, instead of sum, okay, binomial dist is equal to 2, number of successes, comma, trials is 10, comma, probability of any individual outcome being diabetic, 0.1. And this time I'm going to say true for cumulative. And I get the same number I had before for the probability of getting that outcome. So cumulative is going to give it to you for that value and all the values that are less than that value. Okay, so let's think about this for a second. I can use this pretty usefully then, right? So for instance, if I asked you, what's the probability of getting more than 1 person that's diabetic? How would you figure that out? What's the probability of getting more than 1? Well, parse the words very carefully. More than 1 doesn't include 1. It includes 2, 3, 4. It's all of these probabilities here. I could add these together, but normally wouldn't have to. You wouldn't. It might be much larger samples, so it'd be convenient, but much more trials. So more than 1. Okay. So these are the numbers I'm interested in. Numbers I'm not interested in is 1 and 0. So what I could do is I could calculate binomial dist, parentheses, for 1, comma, 10, comma, 0.1, and cumulative true, right? And that'll give me the probability for 1 or 0. Oops. I think I put in a period instead of a comma. true, right? And then that'll give me the probability for 1 and 0. But if I'm interested in the probability for for more than 1, right? Well, then I'm going to have to take that value and subtract it from 1. 1 minus the probability for 0 and 1, which I'm not including, which is 27%. Are you guys comfortable with that? I think I have a couple of problems we can try here. I'm going to try 1 or 2 problems, and then we can call it a night. And you've got some exposure now to doing calculations using the mean and the standard deviation and normal distribution, and doing calculations involving the binomial distribution as well to calculate probabilities. Okay, so let me see what I have here. Binomial problems. Okay. Okay, let's try this one. A study indicates that 4% of American teenagers have tattoos. You randomly select 30 teenagers. What is the likelihood that exactly 3 will have a tattoo? Okay, so what is our probability here? Our probability is 4%, 0.04. What does 30 represent? 30 represent the number of trials, the number of people we're going to sample. And what does 3 represent? 3 represents our number of successes. So I'm going to pull Excel back up. Okay, and I'll push this over here. Okay, let's give this a try. Equals binomial Dist, parentheses, and the number of successes, again, was exactly 3. The trials was 30. The probability was 0.04, comma, and exactly 3. I don't want, if I type in true here, that's going to give me the probability for 3, 2, or 1, or 0 out of the 30 is going to have tattoos. I want false because I only want that exact outcome, not cumulative, just that one outcome. It's about a 9% chance that we would have exactly 3 teenagers that have tattoos. Okay, well, how about the next one? 3 or fewer tattoos. Okay, so that's going to be equal to binomial Dist, parentheses, and I'm going to say, let's see, number of successes is 3, comma, probability is, the number of trials is 30, comma, the probability is 0.04, comma, and now let's make our decision here, 3 or fewer. So we want to see 3, 2, 1, or 0. So if I put in 3 here and say true now, it's going to give me the probability for 3 out of 30, 2 out of 30, 1 out of 30, and 0 out of 30, all combined. And that probability winds up being, it's going to be more than the 9% we had, whatever it was that we had before. It's 97%, right? 4%, you're covering almost all of the possibilities. What's the probability that 4 or more will have tattoos? That means that we're excluding 3, 2, 1, or 0 out of 30. We're only interested in the probability of 4 or more. Well, here we have 3 or fewer. So 4 or more is just going to be equal to 1 minus this value. Okay, so how do you guys feel about this? Do you feel at least a little comfortable about this? Okay, all right. Not everybody's saying okay, but I'll take it. So. Okay, good. So-so's not terrible. So-so's not a bad thing, right? So don't worry about the Poisson distribution. We don't usually cover it in. Levi was lecturing to people that were going to take an advanced statistics course after this. We usually don't cover the Poisson distribution or that more that expect you to work out that more complicated exponential and factorial formula in this particular course. So you don't have to worry about that, but you will be asked maybe a problem that involves these simple binomial distribution questions. Okay, so I am going to call it a night, and we didn't take a break. Well,